Okay, so welcome back to our lecture today as part of our course on the fundamentals of second science and technology. Once more, I'm bringing this to you from IIT Madras. We have had a few lectures already in this course, both the uh, pre-recorded lectures in the first or the 0th week, and then we are now into the first week of this course. So in today's lecture, we will essentially begin with a few details to recap our earlier lecture and then proceed on to the business for today. But before I do that, let me again remind you of the primary sources which I'm referring to, the books by Max Born and Emil Wolf, then the book by Zhengguo Chang and Rouillet's book. And I'm also grateful to Professor Rick Trabino for sharing with me his excellent resources. So we'll recap the previous lecture, the last few actually, some related concepts which we will need in order to make this lecture as self-contained as we would like it to be. And we'll dwell a little bit once again on the physical meaning of the solutions to the three-dimensional wave equation. And in today's class, we will dedicate considerable time and attention to the application of the superposition of electromagnetic waves to the case of the Fabry-Perot interferometer and Etalon, and broadly set up the basis for our understanding of optical resonators. So as far as the recap goes, we can essentially begin with recalling the 1D wave equation, which is d2x d2f by dx2, the partial second derivative of the function f, which ultimately solves the wave equation, minus 1 over the square of the magnitude of the velocity vector v, which is actually the square of the speed of the wave. This is in 1D, as well as then the partial second order derivative with respect to time of this function f, which is a function, of course, of the space and time variables x and t, which light waves essentially and the electric fields as well as magnetic fields will obey this one-dimensional wave equation component-wise because E and B are vectors. And the solution to this equation has the simple form, that is f, which contains two variables x and t, is essentially a function of the type f of x, the spatial variable, plus or minus vt, where v is the speed, it is a scalar, it is the magnitude of a quantity, so it is always positive. And the minus sign here denotes or corresponds to a wave propagating in the positive or increasing x direction, and the plus sign corresponds to a wave propagating in the direction of decreasing x. Of course, this function needs to be twice differentiable. From Maxwell's equations written for the condition where we don't have any free sources, either charges or currents, we can derive the wave equation, the vectorial wave equation for the electric fields, which I show here in the red box, which is del square of E is equal to mu epsilon, the product of the permeability and the permittivity of the medium in which the wave is propagating, multiplied by the partial second order derivative of the E vector field with respect to time. E can also depend on the spatial coordinate or the position vector. So this equation can be derived from Maxwell's equations written in their present form by considering the curl of E and using the Gauss law, which is the divergence of E, which in this case is zero because there are no free sources. And now let us consider the solution to the three-dimensional wave equation. So this is again the 3D wave equation. Of course, I sometimes denote a vector by a bold-faced character or by an arrow on top of the character itself. Here it's bold-faced, so just please note that and allow me to do both. Now, we have here the equation with the Laplacian del square opened out in Cartesian coordinates so that it is d to e by dx2 plus d to e by dy2 plus d to e by dz2 minus mu epsilon d to e by dt2 is equal to the zero vector. So this is just the Laplacian opened out. Now this has the solution, a harmonic periodic solution of the form E x y z t is equal to E naught, the amplitude multiplied by the complex exponential function, exponent of I multiplying k dot r minus omega t. So k dot r minus omega t is the phase term, where the vector k written in terms of Cartesian coordinates, this is 3D space, so it has three components kx, ky, and kz, and the position vector here is xyz. K dot r is kxx plus kyy plus kzz. And the square of the square of the magnitude of the k vector is kx square plus ky square plus kz square. So it's the sum of the components squared up and added. So we know that this solves the wave equation. Why? Primarily because look at this argument of the complex exponent function. It has the form k, there it was x, but this is essentially kxx plus kyy plus kzz in this case, in this coordinate system. Minus, instead of vt, it is omega t, and that works just as fine because we realize that the phase velocity of the wave is omega by k, right? So this has the x minus vt form in the vectorial notation. So we also understand that this wave, a phase point on this wave, say take a maximum, this propagates with a certain velocity if the wave propagates in the forward x direction. This essentially propagates with a velocity v, which we call the phase velocity in this case, which essentially is the ratio of the spatial period lambda, the wavelength, divided by the temporal period tau. So this essentially tells us that a point with a certain phase value essentially moves the distance lambda in time t as the wave propagates. Now the cyclical frequency nu or the frequency nu, both we use this some synonymously more often than not, is essentially 1 over the time period of the wave or the period of the wave. So taking this relation up, v is nu lambda. It's something we will often refer to in this course. So sort of something that you can put in your toolkit for this course. And k, the magnitude of the propagation vector, k is essentially 2 pi divided by lambda. The angular frequency, again, is a quantity we are going to use a lot. The angular frequency is 2 pi divided by the time period. So this essentially has units of radians per second because it's an angular quantity divided by a temporal quantity. And the magnitude of the velocity vector of the wave, or its speed, so to say, is omega by k. Now, waves could have a polarization. In general, either longitudinal or transverse. Polarization is, in this case, it has a working definition of the direction in which the amplitude of the wave oscillates or undulates, as the case may be. So if this oscillation is along the propagation direction, then the polarization is said to be longitudinal. If the oscillation of the amplitude is in a direction perpendicular to that of the polarization, the wave is said to be transverse. Light waves are transverse. So in three-dimensional space, which is all we will deal with in terms of real waves here, we have two transverse directions. If the wave is propagating along, let's say, the z direction, which essentially goes from the left to the right of the screen, you can place the x and y of the xyz Cartesian system such that x and y are perpendicular to z always. So this is essentially the direction of polarization of the wave, and light waves are transverse always. But this brings us up formally to the fact that light waves essentially form a three-dimensional vector field, much like a velocity field formed by the patterns of wind, which are important in meteorology. Now, a 3D vector field, of course, assigns to every point in space a vector. So it's a vector valued function. So light waves have both electric and magnetic fields, the E field and the B field. Now for the considering a Cartesian system with X, Y, and Z as marked here at the bottom left corner of your screen, we can now, based on Maxwell's equations and the wave equation, put out the way in which this wave propagates, which is essentially what is being shown here, the wave propagation in increasing the direction of increasing z, or the positive z direction. Note that the electric field vectors which are in green and the magnetic field vectors which are in blue essentially are perpendicular to each other. This is a consequence of Maxwell's equations, right? Take the same, the typical solution that I'm referring to here, E naught exponent I k dot r minus omega t, and substitute this into the equation which says curl E is equal to minus dB by dt, and you will immediately realize this. That's one way of realizing the fact that E, B, and K form a right-handed triad. That is to say that E, B, and K are mutually perpendicular, and that you can say that the direction of the K vector, the propagation vector, is the same as the direction of the vector resulting from the cross product of E and B, that is E cross B. Not only that, and an even more important point, or which probably is not as often emphasized as it should be, is the fact that the magnetic and the electric fields are always perfectly in phase. Okay, so look at that. The rise from zero to a positive maximum, and the decline of the fields to zero, going through a negative maximum and coming back to zero through a whole cycle. Both the E and B fields are perfectly in sync. There is absolutely no mismatch. This is again a consequence of Maxwell's equations. And just try out the exercise. I told you, I suggested a little while ago, and you will see this coming up, right? So now, but then we dwelt a bit on the physical meaning of this form of the solution to the wave equation, which was E of xyzt is E naught exponent of I k dot minus omega t. The tildes underneath the E essentially remind us that we are using the complex notation, although electric fields are in real fields, real valued vector fields. Okay, we are using it as a mathematical tool, and so we are reminding ourselves of that, right? So if I now consider the solution of the sort of form we had taken up earlier, where the amplitude of the wave is E naught, I will skip mentioning the tildes. You understand what they mean. Exponent I k dot r minus omega t. This wave is called a plane wave. So essentially, what is this concept of a plane wave? We understood that quite a bit in the lecture that in the previous lecture. So if I now figure out a contour of the field maxima as the wave propagates, as is shown here, as the wave propagates along with the k vector pointing in the horizontal direction towards the right of your screen, which we presume is the direction of, say, increasing z or positive z direction. Then if I form a contour of all spatial points at a given time where the electric field takes the maximum value, then this is essentially points lying on a plane. Okay, so why do I say this? Now consider an instant of time at which the wave was here, where my cursor is hovering. That's the maximum of the wave was at this spatial location. It attained a maximum value. So fix that time to be t is equal to some t1. So omega t is a fixed number. So now I'm going to ask the question, let me know all the other points which share the same value for the phase k dot r minus omega t at the instant t1 as it did for my point of interest. That is to say, k dot r minus omega t1 is equal to a constant. So that the solution of all the points for which k dot r minus omega t1 is a constant will constitute this contour. Okay, so I'm actually maybe suggesting you to do a bit of mental math, but I think this is really so trivial in one sense that, okay, this screen is just, I mean, this is really so trivial that I'm pretty sure you can see the fact that kxx plus kyy plus kzz minus omega t1 is equal to a constant. It leads us to the equation of a plane. Okay, so maybe I should just take a few seconds to write this down, that kxx plus kyy plus kzz minus omega t1 is equal to a constant, or kxx plus kyy plus kzz is equal to another constant quantity. This essentially is the equation of a plane in a Cartesian system. Right? The way we denote this pictorially is if we have artistic talent enough to really sketch out these nice rectangles, which I probably cannot challenge myself to do spontaneously, but we could otherwise just sketch lines to emphasize the fact that these wavefronts are planar. The point to remember and note is that the k vector is at all times perpendicular to these wave fronts or phase fronts, right? So that's very important. Even if the contour for any reason were not to be a flat plane, it was curved, since EB and K form a right-handed triad, at every point on the wavefront, the propagation vector is indeed perpendicular to or rather normal, is a normal to a wavefront. Okay, even a rigorous mathematical proof of this is possible. You can, I refer you to the text by Born and Wolf, The Principles of Optics, where this is stated, but again, as I'm doing without much proof, with a little bit of vector calculus, you can show that, right? And the other significant point is that these are infinite planes in the way we have formulated this. This solution is true for all values of k, r and t, right? So this also means that these planar wave solutions of E naught exponent I k dot r minus omega t are infinite wavefronts. And if I consider just any one contour where the electric field was a maximal value, right? Then on this infinite front, you have an electric field through an infinite number of space points having a finite value. And since the absolute value squared of the electric field is proportional to energy or power, this corresponds to a situation of having infinite energy or power. This is, of course, unphysical. So we wanted to spatially limit these wave fronts, which otherwise seem to have a sort of unphysical realization of this concept, leading to infinity in energy. So real beams of electromagnetic waves essentially are far more localized. So we can introduce the localization using, for example, a Gaussian function in x and y, the transverse variables perpendicular to the direction of propagation. So now we write the same solution down, which is E xyzt is equal to now E naught, again the constant amplitude, multiplying the exponent of kz minus omega t. So whatever happened to k dot r, in this case, the k vector is parallel to the z-axis or is along the z or z-axis, right? So kx and ky are 0. kz is non-zero, but kz is then also equal to the magnitude of the k vector k. So we have written this as k multiplying z minus omega t. So that is k rod r, right? Now, so the first and the last term essentially present to us once again a plane wave, okay, where the wavefront is now parallel to the xy plane, the plane that is perpendicular to the z-axis or z-axis, right? But then we have sandwiched in between here a term that modulates the amplitude. Remember, this is a real exponential function. There is no missing I. It's the real exponential function, which is a Gaussian function in two variables x and y, with w being a constant that determines the width of this Gaussian, right? So this limits the spatial extent of the wave, and we no more, as a consequence of multiplying the Gaussian function as a modulation in the transverse coordinates of this wave, we have limited the amount of energy that the wave essentially contains. This is a real wave. It's a typical laser beam, if you wish, and we have a localized wavefront. So a typical laser pointer beam, which you see on the wall, which looks close to what we show in this picture, essentially is a fairly localized wavefront, yet propagating in the z direction, and it is in this description a plane wave. We will encounter later in this course Gaussian beams, which are not necessarily planar, but they actually have a finite curvature to them. Okay, the radius is not infinity for those as it is in the case of the plane wave, if I were to talk about it in the language of spherical wavefronts.